10.1 Sequences as Functions. A definition. This particular chapter is about number patterns, and so we have a definition for a sequence, which is a function in which the domain consists of natural numbers and the range consists of real numbers. I know this definition might seem a little bit confusing, so don't concern yourself too much about it. It'll start to make more sense when we get through the example. Here's an example of a sequence, 3, 7, 11, and 15. Down here we have the notation for how we tend to write about sequences. Lowercase a with a subscript, sub 1, sub 2, and so on. This is kind of like when you learned about function notation. F of x is equal to y. Or maybe you might say f of 2 is equal to 7. So that meant when you put 2 into the function, what you got out was a 7. So x was your input, y was your output. This is very similar, except what you're doing is you're putting in the position. So the position is your input value, and what you are getting out is the term. So the second term is 7. So instead of saying like f of 1 is equal to 3, we don't write it like that. Instead we say a sub 1 is equal to 3. Before we get too far into the sequences, you need to understand the difference between finite and infinite sequences. As you can imagine by the name, finite sequences are sequences that stop. Here is an example of a finite sequence. This is an example of an infinite sequence, which is a sequence that continues on forever. And the only way for you to know whether or not your sequence is infinite or finite is your dot, dot, dot. These are known as ellipses here at the end of your sequence. Arithmetic sequences. These three sequences are examples of arithmetic sequences. So what about them makes them arithmetic? Well, in that first sequence, you'll see that they are all just increasing by 1. So 1 plus 1 is 2, 2 plus 1 is 3, and so on. In the green sequence, they're all increasing by 3. 0 plus 3 is 3, 3 plus 3 is 6, 6 plus 3 is 9, and so on. In the purple sequence, they're decreasing by 5s. 10 minus 5 is negative 5, 5 minus 5 is 0, and so on. So what's happening here is they are all increasing, or the same value is being added each time, even though in the purple sequence we're subtracting, but subtraction is really just adding a negative number. Here's a definition of arithmetic sequences. So this is when you have a common difference. You're always going to talk about sequences with, the common difference with a lowercase d, and this always means that you're going to add to get to the next term. In this example, you need to determine whether or not the sequence is arithmetic or not. Letter A, no, that is not arithmetic. It might look like it is because negative 3 minus 5 is negative 8, negative 8 minus 5 is negative 13, but negative 13 minus 10 is negative 23. Letter B, yes, that one is arithmetic because negative 8 plus 6 is negative 2, negative 2 plus 6 is 4, 4 plus 6 is 10. In this sequence, let's write down first the next 4 terms, and then we're going to graph it. So you can see that the common difference is going to be 2 because this is increasing by 2. So after negative 4, we're going to get negative 2, and then 0, and then 2, and then 4. Supposed to be commas right there. Now to graph it, we're again going to think about this as being kind of like a function, where instead of x, you're going to have your position of the term in the sequence, and then instead of y, we have the term itself. So we only have 7 terms, so the input is just, okay, I said 7, and I wrote 7. 1, 2, 3, 4, 5, 6, 7. Notice these are just natural numbers, and then your output values are negative 8, negative 6, negative 4. These are your terms, negative 2, 0, 2, and 4. So you're just going to plot these on the coordinate plane. All right, I have them now plotted on the coordinate plane, and I do want to point out that one thing that's essential here is do not connect the dots. Okay, this is not a continuous function. This is just a sequence of numbers whose domain is just the natural numbers. We're saying that the sequence is only defined when the position is 1 and 2, not anything between 1 and 2. So don't attempt to connect those dots because then you're saying it is defined between 1 and 2. Now, this question here, how does the common difference relate to a linear function? If you were to connect them, what's the relationship? Well, we see up here that the common difference was 2, and hopefully you can see in this line that the slope would be 2. So the slope is the same thing as the common difference. There is, in fact, some sort of relationship between linear functions and arithmetic sequences, and we'll dive into that more later. your first video quiz question. Okay, in this example, after you read it, you'll see that we want to find the number of performers there will be in the 14th row. Again, I would find it useful to map it out. In the first row, we have 1 performer. In the second row, we have 3 performers. In the third row, we have 5. We want to know what's going to happen in the 14th row. How many performers are you going to have? Now, if we relate this back to the linear functions, as we just said, and we think about this the third row, 5 people, as being like an x1 and a y1, and the 14th row having p performers being x2, y2, then we can plug it into the slope formula. I wrote x2, darn it. Let's say y2 minus y1 over x2 minus x1. We know the slope is the same as the common difference. The common difference is 2 in this case. So we're going to have p minus 5 over 14 minus 3, and we'll solve for p. Okay, I've just solved for p, and I got that there are 27 performers in the 14th row. Yes, there is another way that you could have done this problem. Obviously, like a kindergartner, you could write down the 4th row and how many people, and the 5th row and how many people, until eventually you get to the 14th row and you can see there are 27 people. But this technique that I did is a bit more sophisticated. There is another way to think about it logically, that some students would sort of do what I did algebraically, but they would just figure it out in their head, and that's perfectly fine as well. The kindergartner technique would not work very well if you were trying to get to, say, the 214th row, because that would just take too long. Here we have some examples of geometric sequences. What about them makes them geometric? Well, hopefully you can see that to get from 2 to 10, you're multiplying by 5, from 5 to 10, 10 to 50, multiplying by 5, multiplying by 5. So here you say you have a common ratio of 5. In the next sequence, you're alternating from positive to negative to positive to negative. One way to make that happen is to multiply by a negative value. So 3 times negative 2 is negative 6. Negative 6 times negative 2 is positive 12. Positive 12 times negative 2 is negative 24. So here your common ratio is negative 2. In the third example, we are multiplying by negative 1/2. So negative and a fraction to get to the next terms of the sequence. So here your common ratio is negative 1/2. So down here you can see the definition of a geometric sequence. You should copy this down. It's one that has a common ratio. In other words, you're multiplying to get to the next term. Take a minute and figure out whether or not these sequences are geometric. Yes, this first one is geometric because 8 times 2.5 is 20, and 20 times 2.5 is 50. Your ratio is 2.5. If you're not clear about how to get the ratio, all you have to do is divide the second term divided by the first term, or you can do the third term divided by the second term, and you're going to see that they all equal the same number. Letter B, no, that is not a geometric sequence. If you try to do the division, and 30 divided by 19 is going to be some nasty looking decimal, which is not the same decimal as if you were to do 41 divided by 30. Okay, we're going to find the next 3 terms of this geometric sequence. You can calculate that your common ratio is going to be 1.5. So 22 times 1.5 is 33.75. Multiply that by 1.5, 50.625, and then the next one will be 75.9375. Again, to plot them, you're going to think about their position. The first term is 10, the second term is 15, and so on, and you're going to plot those points. Okay, I went ahead and plotted those points. I just had to eyeball them because, of course, these were decimals that I was trying to plot. Once again, do not connect the dots. Do not connect the dots. This is not a continuous function. This is just a list of numbers. What type of function appears to be graphed here? An exponential function. Holy smokes, there must be some sort of a connection between exponential functions and geometric sequences. Determine whether or not each sequence is arithmetic, geometric, or neither. Letter A. That one is arithmetic. Why is it arithmetic? Because it has a common difference and that common difference is 12. Letter B, neither. It's neither arithmetic nor geometric. There is no common difference or ratio. Letter C, that one is geometric. It is geometric because there is a common ratio, and that common ratio is -2. Last two examples are going to be SAT type questions, so I'd like you to pause the video and give this one a try. Okay, what we can do here is maybe we can find y first. Y is 4 more than 3 times its previous number, which is 43. So you can calculate that y is going to be 133. Then it's going to be pretty easy to calculate z, because z is going to be 4 more than 3 times its previous number, which we just figured out is 133. So z is going to be 403. Now for x, we know that 13 is going to be 4 more than 3 times its previous number, which is x. So you can calculate that x is going to be 3. Then you want to make sure you're answering the question, because they want to know what's the sum of x and z. So x plus z is 3 plus 403, so that's 406. This last example is also an SAT question. Please pause the video, try it on your own first. This is a tricky one. What you're going to want to do is figure out that there's a pattern. The first term is 2, the second term is 5, the third term is 7, and that pattern is going to repeat indefinitely. So in other words, the fourth term is going to be 2 again, the fifth term is going to be 5 again, the sixth term is going to be 7, and so on. So you could easily figure out that the 12th term, so a sub 12, is going to be the same as a sub 6, which is going to be the same as a sub 3, which is going to be 7. Now finding the, sorry, I was just going to also say that you could count that out, right? You can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and see that pattern. You can do that same process in order to find the 91st term, a sub 91, but another thing that you could do is maybe figure out that the 90th term, do you notice this pattern here that the multiple of 3 is 7, multiple of 3 is 7. Well, what's the closest multiple of 3 that's close to 91st term? Well, the 90th term, 90 is a multiple of 3, and that's going to be 7. So apparently your pattern is going to repeat such that you would be going 88, 89, 90, and then you're repeating back up here for the 91st term. So that means that your 91st term is going to be 2. So to answer the question then, the question is what's the sum of the 12th and 91st term? So a sub 12 plus a sub 91, you're looking at 7 plus 2, so the answer there is 9.